Hello everyone and welcome to today's online class for class 11. We are today going to try to do some revisions from the previous chapters that we had already done. The first question in the revisioning we were going to do is this question. The question is from the first chapter known as the basic concepts of chemistry. Calculate the the molality of a solution of ethanol in water the mole fraction of ethanol is in which the mole fraction of ethanol is 0.04. This is the question. Calculate the molality of a solution of ethanol in water in which the mole fraction of ethanol is 0.04. Now, we all know by the definition of mole fraction, which is X of ethanol is equals to N of ethanol divided by N of ethanol plus N of H2. Now X of ethanol represents the mole fraction of the ethanol, N of ethanol represents the mole number of the ethanol, and N of H2 represents the mole number of the water. Now to calculate the molality, the solvent we need to take 100,000 gram. The solvent in this case is water, and as we need to find out the molality, so the mass of the water in this solution we are going to assume it is going to be 1000 gram. Mass of water (1000 gram). Molecular mass of water we all know 18 gram per mole. Now we can easily find out the mole number that is equivalent to 1000 gram of water, which is N of H2O equals to mass by molecular mass, that is 1000 by 18. It will give 55.55 mole. This is the mole of water that is going to be present in the 0.04 mole fraction of ethanol in the solution. Now just by putting this value in the mole fraction equation, we can find out the mole number of the ethanol, which is 0.04 equals to N of ETOH divided by N of ETOH plus 55.55. Now, by doing simplification, the amount that is going to be is N of ETOH, mole number of ethanol that we are going to find is 2.314. Now, this mole number 2.314 of ethanol moles of ethanol present in 1000 gram of water, which is nothing but the basic definition of molality. So we can say that the molality of the solution, therefore molality of the solution equals to 2.314 molal. The second question that we are going to study is from the chapter Structure of Atom. The question is saying calculate the number of electrons which will together weigh 1 gram. Along with this one, there is a second question in this particular question, which is calculate the mass and charge of 1 mole of electrons. Now these are the two questions, very simple questions these are. The first one is saying that calculate the numbers of electrons which will together weigh 1 gram. Now to answer this one, we need to consider the mass of 1 electron. We all know that the mass of 1 electron is 9.11 into 10 to the power minus 31 kg. Now the total numbers of electrons that are given weigh 1 gram. So 1 gram in the unit of kg is of 10 to the power minus 3 kg. So we need to find out how many numbers of electrons are present in this particular amount of this particular 10 to the power minus 3 kg of electrons. Just by doing simple unitary method, we can find this particular answer. Therefore, the number of electrons present ten to the power minus 3 divided by 9.1 into 10 to the power minus 31, and this will give the value nearer to 1.0 9, 8 into 10 to the power 27 electrons. The second question they are asking is to calculate the mass and the charge of 1 mole of electron. Again, we are going to take the mass of 1 electron. Now, the mass of 1 electron (9.1 into 10 to the power minus 31 kg). 1 mole of electron is equal to 6.022 into 10 to the power 23 numbers of electrons. Therefore, the mass of 1 mole of electron (9.1 into 10 to the power minus 31 into 6.022 into 10 to the power 23). This will give the mass of 1 mole of electron, which is 5.486 into 10 to the power minus 7 kg. This is the second question. This is the answer of the first question. And they also asked about the total charge of 1 mole of electrons. For the charge of 1 electron, charge of 1 electron 1.602 into 10 to the power minus 19 coulomb. Therefore, charge of 1 mole of electron 1.602 into 10 to the power minus 19 multiplied 6.022 into 10 to the power 23. This will give the total charge value of 9.65 into 10 to the power 4 coulomb. The next question that we are going to do is from the chapter known as Properties of Atom and Periodicity, that is from periodic table, from the third chapter known, simplified known as periodic table. The question that we are going to study is explain why boron has lower ionization enthalpy than beryllium. This is number 1. This is number 2. Oxygen has lower ionization enthalpy than nitrogen and fluorine. This is the second question. Let's try to do the first one first, which is boron has lower ionization enthalpy than beryllium. We know that in a period from moving to left to right, the ionization enthalpy increases. Beryllium is group 2 element in the period 2. Boron is group 13 element in the same period. So boron is situated at the furthest right hand side in the periodic table compared to the beryllium. So boron should have the higher ionization enthalpy compared to the beryllium. But the question is stating that boron has the lower ionization enthalpy compared to beryllium. Now why is that? The answer lies in their respective electronic configuration, valence shell electronic configuration. The ground state valence shell electronic configuration for beryllium is 1s2 2s2. For boron it is 1s2 2s2 2p1. Along with the valence shell, I also had written the inner 1s2 orbital because this is only one orbital, so I just write it down. Now, when the first ionization happened in boron, in beryllium loses one electron and produces beryllium plus, and the electronic valence shell electronic configuration becomes 1s1. For boron, if the first ionization was to be happened, it will lose the outermost valence shell electron and produces boron plus cation, and thus the valence shell electronic configuration will result in 2s2. Now evidently you can see beryllium was already present in the fulfilled stable valence shell configuration. By the first ionization, that fulfilled valence shell orbital transformed into the half-filled valence shell orbital, whereas for boron, after the first ionization, the boron had gained the fulfilled 2s orbital, the stability of fulfilled 2s orbital. So boron by default try to facilitate this process to gain that extra stability, to gain that extra fulfilled orbital stability, whereas beryllium, though it is situated at the left, try to prevent the first ionization so it can retain its fulfilled stability. That's why the first ionization enthalpy for boron found to be lower compared to the beryllium, because lower energy is required to remove the outermost last electron from boron compared to beryllium. Second question in this particular question that we were doing is that oxygen has lower ionization enthalpy than nitrogen and fluorine. Now, the second question, oxygen is situated in the group 16 in the period 2. Nitrogen is also present group 15 in the same period. Evidently, oxygen should have higher ionization enthalpy compared to the nitrogen, but the question is stating that oxygen has lower ionization enthalpy compared to nitrogen. Now, why is that? Again, we are going to take the help of their respective electronic configuration. For oxygen, the valence shell electronic configuration is 2s2 2p4. For nitrogen, it is 2s2 2p3. So when oxygen loses one electron and produces AO plus during first ionization, the electronic configuration results in 2s2 2p3. Whereas for nitrogen, when it loses one electron, first electron from the last valence electron, it becomes N plus, and the electronic configuration results in 2s2 2p2. In this one also you can observe that oxygen gains the half filled and full filled stability from the electronic configuration, which was not in the in this extra stability state. In fact, the first ionization was happening from 2p orbital, in which the electron is having 4 electron. So by losing one electron, the p orbital, the 2p orbital gains the 3 electron, which is the half fill stability for the p orbital. And thus it is getting this extra stability. Whereas in the nitrogen was in the half filled and full filled stability in the ground state, in the neutral state. By doing the first ionization, in fact, nitrogen is losing its half filled and full filled extra stability. That's why nitrogen try to prevent the first ionization, whereas oxygen facilitate the first ionization, making the entire process more easier. Hence, lower energy is required for the removal of the first electron from the last electron from the oxygen atom, from the neutral oxygen atom, for the first ionization, resulting in lower amount of ionization enthalpy compared to nitrogen. What is happening for nitrogen if we compare the ionization of oxygen with the fluorine? Now, fluorine, the valence shell electronic configuration is 2s2 2p5. It is group 17 element and also period 2. So it is on the right hand side of oxygen. So the amount of ionization that is required, ionization enthalpy that is required by fluorine should be more compared to the oxygen. The question is stating that oxygen has a lower ionization enthalpy than nitrogen and fluorine, meaning oxygen has lower ionization enthalpy compared to fluorine, which is true, which is in accordance with the periodic trend, as fluorine is situated on the right hand side of the oxygen in the periodic table in the same period. So the ionization enthalpy of fluorine is more compared to the oxygen. Not only that, we can also see that by just gaining one electron, fluorine can attain the octet. Hence, fluorine, being a very small atom and having extremely high electronegativity, instead of losing the outermost electron for first ionization is actually it actually try to gain electron. It's actually prevent the ionization. That is also why the ionization enthalpy, the first ionization enthalpy of fluorine is much more compared to oxygen. Or in in opposite, you can say that oxygen has lower ionization enthalpy compared to fluorine.